Okay, here's the next iteration in Josh's mini lectures. Um, I've got the headphones in to keep down the background noise from um, the fan on my computer, which is unhappy with all the things I've got running right now. So what we're going to do is talk about inelastic collisions, and uh, we've got two types of collisions that we'll be dealing with this semester. That's collisions, interactions between objects. So far, we haven't really dealt with interactions between objects unless they're in contact with each other and staying in contact with each other. So now we're talking about an interaction form of a collision. So two objects that are apart come together and interact, and then something happens after that interaction. So an inelastic collision is one in which the objects hit and stick. That would be a perfectly inelastic collision. And a perfectly elastic collision is one in which the particles hit and bounce in such a way that the total amount of kinetic energy is conserved. Um, we did energy, then we're coming back to momentum, then we're going back to energy again because of the way that things are done in the lab in the class. But right now, we're just going to talk about inelastic collisions, and we're going to use the conservation of momentum to help us understand that. And so if the colliding objects are part of your system, then the momentum of that system and the total momentum of those objects is conserved because the collision, that interaction, only involves forces on each other and between the objects that are within the system. It's not an external force from outside that's coming in that can change the momentum of the whole system. So one thing hits another, that's a force on that, but there's an equal and opposite force so that the total momentum of the system is maintained. So if colliding objects are within the defined system, the total momentum of the objects is not changed by the collision. And this is kind of an amazing thing on the one hand. On the other hand, the universe would be a very strange place if this wasn't true. But it means it doesn't matter what happens in the details of the collision. If it's a bouncy ball bouncing off another bouncy ball, or if it's two lumps of clay coming together, the total momentum is conserved in both cases, regardless of what happens. Two cars crash into each other, there's all sorts of sound and terrible things going on, but the momentum of those cars after the collision is the same as before the collision. The only thing that can change it is outside forces, which in that case might be, for example, friction from the road acting on them. So let me just write that out. It's not changed by the collision. So that's what's shown in the slides here. Two objects approach and collide, and they stick and move together. That's what makes it an inelastic collision, the fact that they stick together. So beforehand, they each have some momentum. Object one has got momentum to the right. Object two has got momentum to the left. Afterwards, they are together as a common object with a single mass, and they're moving off to the right with some velocity. So the slides work you through an example, and we'll just go ahead and do our own example ourselves because you can read the example that's worked out in the book and the slides just as well as I can. In this example, we have a 10-gram bullet fired into a 1 kilogram wood block where it lodges and sticks. Subsequently, the block slides 4 meters across the floor. What was the bullet's speed? So in all of these things where we're using a conservation principle to figure things out, whether it's conservation of energy or conservation of momentum, we sort of have a before and after. We know the total energy before something happened, like a ball is at the top of a hill, and then we want to know what's going on when the ball's at the bottom of the hill, so we don't really care how it got there. It's just after it rolled down the hill, whatever path it followed. Let's take a look at the energy then. So in this particular case, we've got a block and a bullet with some initial velocity that's unknown. That's the bullet. And the block is sitting on the floor with a coefficient of friction with the floor that's given to us as 0.2. That's my mu k is 0.2. We're told that the mass of the block is 1 kilogram and the mass of the bullet is 10 grams, which is 0.01 kilograms. That's the unit conversion for that. And so what we know is that momentum is conserved. Let's go ahead and draw the after picture. Afterwards, immediately afterwards, we have the bullet has gone into the block, and I'm going to call this V, I'll call it VF for now. That's the block. VF is the velocity of the block plus the bullet immediately after the bullet hits the block. Why am I emphasizing immediately? Because there's friction between the block and the floor. So what happens after the bullet hits the block is there's a force acting on the block. That is an external force that can change the momentum of the block. Ultimately, what's going to happen? The block comes to a stop. When it stopped, that means there's no more momentum. The velocity is zero. So the momentum has gone from something to zero. And the reason it did that is because there's an external force acting on it. That external force is friction of the floor on the block. So immediately after the bullet hits it, friction hasn't done anything yet. So we want to figure out what that velocity is. Then we know it travels for 4 meters. So we're going to come to that. We're going to define our system is the bullet and the block. Okay, and hang on one second. I'm just making sure I don't have people waiting in my office hour right now, because that's when I'm recording this and I don't. So our initial momentum is just the mass of the bullet. I'm using a little m and a little b for that, times the initial velocity of the bullet, and I don't know what that initial velocity is. My final momentum, and by final, I mean before external forces are acting on it, okay? It's going to be the same number, but that is now the mass of the block, big M, big B, plus the mass of the bullet, little m, little b, times this thing I'm calling VF. So those two things have to be equal. So I have m little b times VI equals m big B plus m little b times VF. Well, I know the masses, but I don't know either of those velocities. And what I'm trying to find out is, what is this little VI equal to? How fast was the bullet going? But there's one other piece of information I have. And that other piece of information is that the block slides 4 meters across the floor. Okay, how can I use that piece of information? I know that the coefficient of friction between the block and the floor is 0.2. That means there's friction. That means the thing is coming to a stop. So let's draw a free body diagram. of the block and the bullet together, and it starts moving to the right with a speed that I called VF from the previous page. That's the speed it had just after the bullet hit it. There's friction on it. Oh, I shouldn't have drawn this that way. Its initial velocity, VF, is like that, but the forces acting on it are friction, kinetic friction to the left, of course its weight down, and the normal force up. Okay, those are the forces acting on it. This thing has, therefore, a net acceleration to the left in the opposite direction of its velocity here, so it's going to come to a stop. After traveling 4 meters. So this is now a kinematics problem. If we can figure out this VF, then we know everything else in this equation for conservation of momentum. We know the m's. If we know VF, then we can get VI. So the VF is actually the initial velocity for the motion of the block sliding across the floor. I'm going to still, well, let's see, I'll call that, we set up our kinematic properties as usual. There are 5 of them. This VF here is 0. This is why I was hesitating about what I call things, because now I've got myself a little bit of a mess. This thing, maybe you would call it VF with a capital F or something like that. This is the final velocity from the momentum part of the problem. This is after the bullet hits, but before it slows down. So I apologize for the potential confusion here about VI and VF. Basically, we're doing this problem in 2 parts. First, the bullet hits the block and starts the block moving. In that process, momentum is conserved. Then you just have this thing, a piece of wood with a bullet stuck in it, that is sliding across the floor, and it comes to a stop because there's friction acting on it, and that's a kinematics problem. So we're starting now, now we've set that up, we're now going to the kinematics problem. We know it goes, zoom out. We know it goes 4 meters, and we're looking for how fast it was going at the beginning before friction slows it down. So it's looking, challenging here. We have 2 numbers. We know it comes to stop. We know it goes 4 meters. We don't know how fast it was going to begin with. We don't know the acceleration or the time. So we need to know one of those 2 things. How are we going to figure that out? Well, we can go after the acceleration because we know the force that's acting on it and we know the mass, right? So what's the acceleration? The forces acting on this thing in the horizontal direction, which is the direction that it's moving, the sum of the x forces equals the mass times the x acceleration, which is what we need to solve the kinematics part of the problem. Well, there's only one x force, that's Fk, is equal to ma. I'll just call it a. There is no vertical acceleration, so I'll leave that alone. And we remember that Fk is mu k times n, which is equal to ma. And we know that the sum of the y forces on this thing is 0 because there's no acceleration in the vertical direction. And what are the y forces? N minus W equals 0. That's N minus mg equals 0. That gives me N equals mg. So now I have N. I can substitute that into my x equation of Newton's second law. So I have mu k times mg equals m times a. I know the mass, but I don't need to. Cancels out. So that gives me the acceleration is mu k times g, which is 0.2 times 9.8. Ta-da! I have now a number for the acceleration. So the acceleration is 0.2 times 9.8, and let's just get our digits correct on that. If I can type here, 0.2 times 9.8 is 1.96 meters per second squared. So I'm just going to redraw my chart here with these parameters. It goes 4 meters. I'm looking for this velocity, which I call VF. This final velocity is 0. And the acceleration is minus 1.96. And I got to put that minus sign there because it's in the opposite direction of the displacement. The thing is moving one way, but it's accelerating in the other direction. We had that in our free body diagram, which you can see here at the top. It's moving to the right the way I drew it, but the acceleration is to the left. So the displacement is to the right, the acceleration is to the left. They have to be opposite signs, those two numbers. This is the number I'm going after. So I look at my sheet of paper with my equations on it, and I discover that 2ax is vf squared minus vi squared is the equation that I want. This is then 2 times minus 1.96 times 4 equals minus v big F squared, because this thing here is the 0. That's this guy. That's how fast the block is going after it's come to a stop. So the minuses cancel. That gives me VF is the square root of 2 times 1.96 times 4. And that equals, let's find out, square root of is 3.96 meters per second. That's how fast the block is going immediately after the bullet hits it, but before friction has started to slow it down. So now I go back to my statement of conservation of momentum. Which was that 0.01, the mass of the bullet, times VI, the velocity of the bullet, which is the thing I'm ultimately trying to figure out here, is equal to 1.01, the mass of the block plus the bullet, times 3.96, how fast those two things are moving after the fact. That then gives me VI equals 1.01 times 3.96 divided by 0.01, or VI equals, let's see what our answer is. .400 meters per second. So this is cool because what this means is you could figure out how fast a bullet is shot out of a gun by firing it into a block and just measuring how far the block moves as it slides across the ground and knowing the mass of the block and the coefficient of friction. for that particular material. So it's a very simple kind of measurement to make. So you can think about, you can also, this is how, for example, car crashes can be analyzed. You can look at the skid mark of the rubber on the road, and we know the coefficient of friction between rubber and um, concrete or asphalt, and you measure the length of that skid mark. That tells you the displacement. You know the final velocity is 0. You can figure out the acceleration because you know the coefficient of friction and know what kind of car it was or estimate. You can then get the acceleration and you can figure out how fast was that car going when it stepped on the brakes. And then that gives you forensic evidence that says, oh, that person was speeding, for example, when he stepped on the brakes or the car started skidding. So cool stuff. That's inelastic collisions.